When I look at the night sky, I feel awe in front of the infinity of the universe. But how far can we actually see? Simple telescopes help us observe stars, planets, and even other galaxies. But what's beyond our visible limits? To break through these boundaries, humanity created the most advanced space-exploring instrument, the Space Telescope. These incredible machines reveal not only deep space, but also the history of our universe. Have you ever wondered how space telescopes show us the incredible views of galaxies and stars located billions of light years away? But before answering this question, let's see how an ordinary reflecting telescope works and why it uses mirrors instead of lenses. The main component of such a telescope is the primary mirror. It's large and concave, usually parabolic, and its job is to collect and focus light from distant objects. The light from a star or galaxy hits the primary mirror. The primary mirror focuses it into a single point. At this focal point is a secondary mirror, redirecting the light into an eyepiece or camera. The eyepiece or camera magnifies and captures the image. This design makes the telescope compact and convenient. But what's the main advantage of mirrors? Let's take a flashlight and shine it onto a lens. When the beam of light hits the lens, it refracts. Simply put, the light splits into different colors, each color focusing differently, causing chromatic aberration or blurry images. Sure, solutions exist to minimize chromatic aberration, but eliminating it entirely is impossible. That's one reason lenses aren't used in space telescopes. Another reason is that lenses are challenging to make large since they can deform under their own weight. Imagine how enormous and heavy lenses would be for space telescopes if engineers managed to make them. Mirrors, on the other hand, reflect light independently of color, keeping the image clear. Moreover, mirrors are easier to make larger. For instance, the Hubble telescope's primary mirror has a diameter of 2.4 meters, capturing images in extraordinary detail. Telescopes using mirrors are powerful tools for studying the universe because they don't suffer from color distortion. So, why do we need space telescopes, and how do they help us explore the universe? Imagine yourself observing stars through a powerful telescope on Earth. Even under perfect conditions, high in the mountains, far from city lights, Earth's atmosphere still interferes. It acts like uneven glass, refracting, scattering, and distorting the incoming light. This is exactly why stars twinkle at night, and why ground-based telescope images often lack sharpness. But that's not the only issue. Our atmosphere also blocks most ultraviolet and infrared radiation, precisely the ranges in which many celestial objects emit their strongest signals. This is where space telescopes become essential. Positioned beyond Earth's atmosphere, they're completely free from its distortions and can observe in wavelengths that are inaccessible from the ground. One of the most famous examples is the Hubble Space Telescope, which has captured incredible images of distant galaxies, star clusters, and nebulae. These observations have profoundly expanded our understanding of star formation and galaxy evolution. Another crucial advantage is stability. In space, there's no interference from clouds, wind, or daylight. This allows telescopes to operate continuously, 365 days a year, collecting vast amounts of valuable data. But how many space telescopes are currently exploring the universe? At the time of making this video, there are about 30 active space telescopes in orbit. Each of these telescopes contributes to the development of astronomy and expands our understanding of the universe. This is only a short list of existing telescopes. Hubble is one of the oldest operating telescopes. Launched in 1990, it has been active for over 34 years, greatly exceeding its original 15-year mission lifespan. But a telescope isn't just an instrument for observing stars. It's actually a time machine. It's all about light. Light is our primary messenger from space. It travels at an incredibly fast but finite speed, roughly 300,000 kilometers per second. However, cosmic distances are so vast that even light takes time to reach us. Let's look at an example from our own solar system. This is our Earth. The distance from Earth to the Sun is approximately 150 million kilometers. That means sunlight takes about 8 minutes to reach Earth. So, when we look at the Sun, we're actually seeing it as it was 8 minutes ago. But consider Alpha Centauri A, the nearest star to us. It's 4.3 light-years away. This means we're observing its image from more than 4 years ago. Now, imagine observing a galaxy that's 1 billion light-years away. Its light has traveled toward us for 1 billion years. It's like opening a book filled with stories of events that happened long before our time. But that's not all. Distances in space are so enormous that we must also consider other phenomena, such as the expansion of the universe. This expansion stretches the incoming light, shifting it from visible to infrared wavelengths, a phenomenon called redshift. By observing this, scientists can study what the universe looked like billions of years ago, shortly after the Big Bang. For example, the James Webb Space Telescope can peer into the darkest corners of space, capturing light from ancient galaxies formed during the universe's earliest stages. It's like looking back at the cosmic childhood of our universe. But have you ever wondered why we see only a small portion of light, even though the electromagnetic spectrum is enormous? Our eyes are adapted specifically to visible light, covering wavelengths from about 380 to 750 nanometers. But why this exact range? It's because this range perfectly matches conditions on our planet. Solar radiation is most intense within this spectrum, and Earth's atmosphere lets it pass through almost unhindered. There are also physical limitations. Ultraviolet rays contain too much energy and can damage eye tissues, while infrared rays, in contrast, are too weak to activate our photoreceptors. Additionally, our retina is equipped with rods and cones, cells specifically tuned to detect visible wavelengths. Yet technology opens new horizons for us. Infrared cameras allow us to see the heat emitted by objects, and ultraviolet cameras reveal what bees see naturally. Space telescopes, like the James Webb, operate similarly. They help us explore beyond visible light, investigating previously invisible regions of the universe. Now let's understand how space telescopes work and what makes them different by comparing the Hubble and James Webb telescopes. Even though these telescopes operate differently and are designed for distinct scientific goals, the basis of every telescope is its mirrors. Their main task is to collect light from stars, galaxies, and other objects. The larger the mirror area, the more light it can gather. This becomes especially important when observing extremely faint and distant objects. Hubble's primary mirror has a diameter of 2.4 meters. It's parabolic, which allows it to effectively focus incoming light onto a single point. The light is then reflected onto a secondary mirror and finally directed into cameras and spectrometers, which record visible, ultraviolet, and near-infrared wavelengths. The James Webb Telescope takes an even more innovative approach. Its primary mirror consists of 18 hexagonal segments, each coated with a thin layer of gold. These segments operate together as one large mirror, automatically adjusting their alignment to create a perfect reflective surface. Thanks to this design, Webb's primary mirror reaches an impressive diameter of 6.5 meters, almost 3 times larger than Hubble's. But size isn't the only factor that matters. Webb's unique capability lies in capturing infrared radiation, enabling it to study cold objects, star formation, and galaxies at the earliest stages of their evolution. To achieve this, its mirror is cooled to temperatures below -220 degrees Celsius, minimizing its own thermal radiation to avoid interference. This allows Webb to observe distant galaxies and star systems previously beyond our reach. Another key difference is their orbital placement in space. Hubble orbits relatively close to Earth, at around 540 kilometers altitude. While this helps Hubble avoid atmospheric distortions, it requires periodic maintenance missions. In contrast, James Webb is positioned at the second Lagrange point, L2, one of 5 special equilibrium points in space where gravitational forces from 2 large bodies, such as Earth and the Sun, balance out. This allows a spacecraft to maintain a stable orbit. L2 is located along the Earth, Sun line, opposite the Sun, roughly 1.5 million kilometers away from Earth. At this point, Webb can orbit the Sun in sync with Earth, maintaining a constant relative position. This strategic location provides uninterrupted views of space, free from shadows caused by the Earth or Moon, and offers stable temperatures ideal for infrared observations. A large sun shield further ensures minimal thermal interference. But capturing an image of a star is just half the job. The image must also be sent back to Earth. To do this, telescopes use antennas that transmit data via radio waves. Since the Hubble Space Telescope is located in low Earth orbit, it easily transmits data directly to processing centers on the ground. However, the James Webb Telescope is located 1.5 million kilometers away from Earth, making its communication system especially sensitive. Signals from Webb are received by the Deep Space Network, a global system of ground stations located in the USA, Spain, and Australia. This worldwide network allows continuous communication with the telescope around the clock. The transmitted data first arrives at scientific facilities, such as the Space Telescope Science Institute in Baltimore. Here, it undergoes processing, analysis, and storage in specialized archives, accessible to scientists worldwide. But the data we receive isn't the colorful images commonly seen in news reports or scientific magazines. Instead, it's raw digital information that requires substantial processing. First, noise and defects caused by cosmic rays or detector imperfections are removed. Then, the data undergoes corrections, and unnecessary artifacts are eliminated. The next step is combining images taken through different filters. This produces the colorful pictures filled with extensive scientific information. By analyzing the spectra of light, scientists can determine chemical composition, temperature, and velocity of celestial objects. Images of distant galaxies provide clues about how the universe formed billions of years ago. Hubble and James Webb are 2 remarkable telescopes that complement each other perfectly. Together, they allow us to explore and understand the universe in greater depth, observing objects at different stages of their evolution and revealing previously inaccessible cosmic mysteries. If you enjoyed this video, don't forget to subscribe. Share your idea for a new video in the comments.